I was kind of taking a look at that output. So if I didn't tell you the test statistic, all you would do is for this variable, take the coefficient divided by the standard error. Okay. Now, if I left off the standard error, you now can't find the test statistic. What's the third thing you could use other than the test statistic and p-value to tell me if you can reject the null? So here I can only make a statement at one level because it only displays to me by default that 95% confidence interval. Why can I reject at that 95% confidence interval? Because it's telling me with 95% confidence, this is the true value of the coefficient. It doesn't include 0. And that's always what we start out assuming these coefficients are equal to. So if 0 isn't in my range, I can reject that as a possible true value.
Couldn't you find a standard error by using the confidence interval? Because it's always the...
If you can remember the correct test statistic, yes, you could, right? Now, for me, I mean, you could do that. Find the standard error, find the test statistic. If you just look at the confidence interval, that'd probably be a little bit easier.
Right? Yeah.
Yep, but technically you can, right? Because how do we build this confidence interval? So this is where you can kind of go up here, where we're looking at. Here's my confidence interval. It's always going to be that coefficient estimate plus or minus we call the margin of error, which is that test statistic that gives you the desired alpha over 2 in the tail, which would be our critical values essentially, and multiply that by our standard error. So if I know what the test statistic I want is for the 95% confidence level being 1.96, I know the coefficient, you could tell me what that standard error is. Let's say I left out the coefficient. Okay. Well, there you have to use kind of those confidence, right? So kind of simple linear regression. Hopefully that's not too bad. Let's then go to thinking about what if I have a naive regression where I've left out an important omitted variable. So here I'm just going to assume that I left out male. Okay. So I've got kind of the words of what we're doing here. And if we have the data, we can run that regression, right? Once we include that additional omitted variable, we've eliminated the bias that existed in our coefficient on body weight. But let's think about how could we maybe put a sign to this bias? Maybe not calculate the actual value, but at least put a sign to it. Let's say, hopefully this doesn't screw us up here again. So I'll go in the formula sheet to kind of show you where this is. But if I run this regression where I've got kind of total weight lifted, and I was trying to predict that with body weight. Okay, I'm just kind of abbreviating things here. My bias is going to always be the coefficient of the variable that I omitted times the covariance of the variable that I'm worried about the bias in. Now here I only had one, so I only have to worry about that one variable. If I had additional controls, I could ask you about the omitted variable bias in any of them, right? So it's the covariance of that variable I included and this variance I omitted, which was male. So beta 2 here, if it helps to kind of think about, you could think about this as the coefficient of that second variable we excluded from our regression. And then here's where it gets kind of hard to remember, but I'll show you when we're in the formula sheet to kind of remind us of this. It's then going to be divided by the variance of the variable that I did include in my regression. That's not quite intuitive. You might jump to thinking about, okay, I want the variance of the variable I omitted. That's not the case. Okay. So this is my bias equation. And here's where I could ask you to give me a description, and I would grade it accordingly. I'll try to use examples where I think the assumptions are obvious, right? So here, if I'm thinking about, if I did instead include also this male dummy variable. Well, I'm not trying to be like, sexist or anything here, but it's just a fact of biology. Males tend to have higher muscle mass, right? So if I'm thinking about how much weight they can lift it, if I did include male, what would that coefficient on male be? Likely positive, right? So if my bias, if I did include that male variable, it would have a positive effect on my Y variable, total weight lifted. Now, what would I expect the covariance of body weight and male to be? Once again, just biology across everything. Humans, deer, and most species, the male is always larger or would weigh more. So what would I expect the covariance between male and body weight to be? Positive. What are variances always going to be? What's the lowest variance I could ever see? No variance or 0? So anytime I have variation, the variance has to be positive. The sign of that denominator will never be negative, right? It's a variance, it has to be positive. Okay. So here, what would the sign of my bias be? Positive times a positive over a positive. That bias we would expect to be positive. So when we run this simple linear regression, our coefficient on body weight is going to be 2 what? Well, if it has this additional bias built into it, right? So when I run my naive regression, I'll get the true effect of body weight, but then plus this bias, which we said was positive. So my estimate's going to be too high if I omit this important variable. So fingers crossed. There we go. Okay. So if I'm thinking about that bias should be positive, right? And this was, I think, once again, I try to give examples where the assumption should be obvious. But if you would have told me, like, let's for some reason you said you think that females on average have higher body weights, I grade it accordingly, right? If as long as you state what that assumption is about the covariance, I would kind of grade that accordingly, right? Now, we can actually look at it because we have the data. So if I did include that male variable and I run this regression, right? If I have my naive regression and the one where I've now included that omitted variable, how would I determine the bias? So I could say whether it's positive or negative, but I can actually, if I did this, I can tell you what the actual value is. Why? Because once I include that omitted variable, what have I done to the bias? I've eliminated it. So this coefficient had the bias built in. I've now eliminated it. So what was the value of that bias? Approximately 2. All right. Now, instead, I didn't give you this original naive regression, and I gave you output that looked like this. And I also gave you this command and the following output. Right? How would I determine the size of my bias? I don't have that naive regression to compare to anymore. Well, we already had the equation set up. So if I look at my formula sheet, it reminds me, if I omit an important variable, it would have this bias built in, which is the coefficient of the variable I omitted, times the covariance of the variable I included and omitted, divided by the variance of the variable I included. Okay? So when we're looking at state output, how do I find the coefficient of that variable I excluded originally? Well, that variable was male, so that coefficient is simply what? 198, approximately. Right? What's the covariance between body weight and male? How do I read this output? So if I want the covariance between body weight and male, that value is 5.4. What is the variance on the variable that I included that wasn't this omitted variable I was worried about? Well, the original variable I had in that regression was body weight, right? So I'd want to be using this value as the variance of the variable I did include, right, if I'm trying to calculate this bias. So here I've got what? So, oops, I'll minimize this for a second. I'll kind of scale this so I can kind of see what I'm doing, right? So if I wanted to actually calculate what that bias is, I'm taking the coefficient of that omitted variable. If I instead had included it in my regression, so if I round this, it's about 198.67, I'd multiply that by the covariance between that variable I omitted and the variable that I did include. And I would then divide that by the variance of the non-omitted variable, right? Which was the original variable we had of body weight. Now I'm rounding here. So if I hit this, remember display just does math for us. Sure enough, what value am I getting? Approximately 2. Now there'll be some rounding error there, but you know, when it comes to exam, I'm not going to grade you out to the 4th decimal. As long as you're showing your work, I can understand that you're doing it correctly, right? And I'm not going to grade on rounding errors, right? So that's how we would determine the omitted variable bias. Whether I run the original regression that leaves out that omitted variable, or I and kind of compare it to when I do. Or if I only showed you this output, I didn't show you the naive regression, but I also gave you this covariance matrix, you could determine the size of the bias that way as well. I can guarantee you'll have a question or two that looks like this, either to determine the sign of the bias, or if I give you some data output, actually calculate the size of that bias. Okay? Any questions on that? Now's the time to ask questions. We got today and Tuesday before the exam, right? Okay. So the next thing we can kind of think about is a more recent topic, which is we're talking about kind of joint significance. Okay. So if I instead want to compare this to, so I'll start with this regression where I've included body weight and male. Okay. I'm going to come down here and now include two additional variables, which one was like this identifier for whether or not they could use any assistive equipment, right? So even before I run this regression, what would I expect the sign on that to be? So when I have a dummy variable, right, the coefficient on that variable is the predicted change in my y variable. So if this is for when they can't use any assistive equipment, what would you expect the amount of weight they can lift? It would be lower, or that coefficient would be negative. Okay. Now, age, I don't know for sure, but what would be the interpretation, right? Here's where we want to start to be able to give interpretations of any coefficient. So from this regression, what would the interpretation of that coefficient on age be? So we always start out, if it's a 1 unit increase in that variable, so being 1 year older, it's the predicted change in our y variable. So as this person gets 1 year older, what is the predicted change in the amount of weight they can lift? Now, I would expect that's likely negative. The older you get, you can lift less, right? You're weaker as you get older, but I don't know. I have to run this regression, okay? Now, what did I forget to add in my interpretation there? Because we're no longer looking at simple linear regression. So that's still the way I interpret it, but
holding all these other variables constant.
Holding all these up. So if I ask you to interpret a coefficient from a multiple linear regression, in order to get the full points, you need to include holding all the other variables constant. That's a very powerful statement, right? So we want to make sure when we're interpreting these multiple, don't forget that from multiple linear regression interpretations, okay? So if I'm thinking about joint significance, that's where I wanted to not just test the individual significance of one variable, like we've already talked about earlier, but adding in both variables simultaneously. So we said, what can we do? Well, I could run the test command, right? So for example, and this might be helpful if we're thinking about that last question on the problem set, which is due at the end of the day tomorrow, right? So if I run this joint hypothesis test, whoops, I've got to run the regression first. I get a huge test statistic, right? And the p-value is basically small. So can I reject, what am I starting out when I do this joint hypothesis testing? I'm assuming that both of these variables coefficients are equal to 0. Or essentially, that adding these variables in had no additional predictive power about my y variable. So if I reject that, what I'm saying is that by including them in the model, that does increase whether, the accuracy of my predictions. Or both of these variables simultaneously look like they do have an effect on my y variable. Now, let's say on the exam, you can't run the test command, right? That's an issue. What can I do, right? Well, if I have this regression where I left out age and then this raw category for no assistive equipment, and then I showed you the output where I do include those. If I go to my formula sheet, what we're really doing with that joint hypothesis testing is saying, did the R squared increase by a statistically significant amount when I included these variables? So here, as a reminder, this is where you have this formula sheet, but you have to remember what these things represent. So R squared, right, is the proportion of variation we can explain. Now the unrestricted model, so there are no restrictions, that's where we've included all of the variables. The restricted model was where we left out that age and raw category variable. So we can get those R squareds from the output we just looked at. Now, the other things I'm going to need are N. N in all cases, no matter what we're looking at here, should represent my sample size. Q is going to be the number of restrictions or the number of variables that we left out or are doing this joint hypothesis testing for. So in our example, Q was 2. I could give you an example on the exam where I ask you to test the joint significance of 3 variables, in which case your Q would be 3. So here, the only other thing I need is K. So this is where, make sure I have this written down as I'm studying. K actually represents, you could almost write this as KU. It's the total number of variables that I've included in my unrestricted model. Okay, so it's not going to be 2, it's going to be 4, the number of variables in that unrestricted model where I included everything. So really here, it's just math, right? I can get the R squared from my unrestricted model. I can get the R squared from my restricted model. Now notice, as I add in more variables, if I ask you this question on the exam, this has got to be one you get right. As I add in more variables, what has to happen to the proportion of variation I can explain of Y? Or what has to happen to my R squared? Has to go up, right? So as I add in more variables, sure enough, my R squared went up by about what? 0.04, or I can explain 4% more variation. But when we're doing this joint hypothesis test, what we're saying is, I know that if I add more variables, I can always increase my R squared. But am I increasing it at a kind of, if you want to think about it, a statistically significant amount per variable I've included, right? That's why we kind of divide by Q there, okay, in that F statistic calculation. So I have my 2 R squared values I need. My sample size is 10,000. It's pretty high. And then I've got what? K was 4, and then the number of variables we left out in the restricted model was 2. Now, before we actually know, so what I could do here is I'm really just kind of using, I could generate that variable, or I could simply use that display command to do the math for me, right? Now here, I think I originally had this a little typo there, where the number of variables in that unrestricted model was 4, okay? So here we'll kind of get rid of this. We're going to have the display command. It should just show us that F statistic. I found the R squared from, oh, these values are a little off because I changed the data set. So we're going to have to change these, right? So this is what? 6827. The R squared from our restricted model was what? 6437. I forgot I changed this data set for you. We had 2 restrictions. Now, here's where we have to make sure we're paying attention to the formula. Our joint hypothesis testing here, we're using the R squared of the unrestricted model. Okay? So the R squared from the unrestricted model was where I included all variables, which was this 0.6827. Okay? And then my sample size, this is where I ran it for a huge data set, but I knew in class that might take too long. So I've limited it now to 10,000. Okay, was our sample size. What did I type in wrong here? Oh, wait.
No, it's the end. The 2.
Oh. There we go. Right. So if I then kind of run this, hopefully I get, okay, pretty close. I'm a little bit off because I was rounding things here, right? If I was able to use state on the exam, I could be very precise. It doesn't have to round. But if I asked you this question on the exam, you can kind of plug those values in and determine what that test statistic is. So once again, this is something I might likely expect you to be able to do on the exam. If I give you the regression from the restricted model and the unrestricted model, you should be able to, especially with that formula sheet, calculate that F statistic. So anything less than a graphing calculator. Now, if I was doing this, just a test taking thing, in order not to make parentheses issues, I'd try to break this down, right? Instead of trying to get this all entered into my calculator at once and worry about parentheses, I'd probably calculate this value, divide it by Q, put it in that value, create this value, create that, right? I kind of try to break it down to steps just so I'm not making like order of operations errors there. Okay. That's just a test taking thing, right? Now to kind of make this point, let's assume I gave you a question where I said, let's assume you ran this restricted and this unrestricted model. Okay. So our equation for that F statistic was the difference between the R squared of our restricted and unrestricted model divided by the number of restrictions, 1 minus the R squared from the unrestricted model divided by N minus K minus 1. So I went through these things last class. All of them would be fair game for me to ask. Okay. So let's just assume for a second that my restricted and unrestricted model, I found the exact same R squared values, right? Regardless of the sample size or the number of restrictions. So I give you that assumption. So basically, I'm fixing these values. If I'm looking at an unrestricted and restricted model where I've increased the number of restrictions, right? I'm doing a joint hypothesis test now, not for 2 variables, but maybe I want to do it for 3 or 4. What is that going to do to my F statistic? It's going to increase Q. What's going to happen to this fraction? If the denominator is larger, this fraction goes down, right? We need to remember how fractions work, right? If the denominator is larger, I'm dividing by a larger value, this is going to go down. So if my F statistic decreases, remember for our F statistic, the p-value is only going to be the area to the right because we know as we add in more variables, our R squared has to go up. So we've got a one-tailed test, okay? So if I find a smaller F statistic, what's happening to the area to the right or what's happening to my p-value? My p-value is going up. I have a larger area in that tail. If my p-value is higher, is it more or less likely that that p-value is less than our threshold or kind of benchmark alphas? So it would be less likely I reject. So when I do joint hypothesis tests for more variables, it's going to be less likely that I can reject that null, that they have no joint significance. Because I said another way to think about this joint hypothesis test is, did it increase my R squared per variable I included by a statistically significant amount? So if I find the same increase in my R squared, but I've had to use more variables to do it, that F statistic kind of gets penalized for that. Okay. Any questions on this? Yeah. So not that they're the same, but assume that I found the same values, but using a higher number of variables or having more restrictions, right? Because as I added more variables, what's likely to happen to the unrestricted R squared? It's going to get higher and higher. So I would kind of have to give you that simplifying assumption that assume the unrestricted and restricted R squared don't change, but I found the same values using a higher number of restrictions. Okay. Any other questions before we keep going here? Now, once again, we could think through these other things as well, and I'm likely to do something like this. So let's say instead, those original numbers I had were, yeah. So I mean, I can't, right? Like I have given you a simplifying assumption because if I run this with an additional restriction, what's going to happen to these values? They're going to change. I mean, I can make it harder if you want, right? Or if we have more restrictions, even though it's going to be penalized here, I might find a higher. So I have arrows going in a different direction, which now a possible answer could be indeterminate, right? But here, all I would tell you is assume these have stayed the same. What happens if the number of restrictions changes? I can reproduce that just with values, but like with the actual data, I can't, because with the actual data, as I add in more restrictions, this will change, right? Does that make sense? Now, what you could reproduce for yourself is if I have a smaller sample size. So in general, it doesn't matter if we're looking at joint hypothesis testing, individual coefficient hypothesis testing, or hypothesis testing for a sample mean. Having a smaller sample size means I have less data. So should my results be more or less likely to be accurate? Less likely. So in all cases, I should be less likely to reject the null. We can walk through why. If n increases, what happens to this fraction? Right? So it's going to become smaller. Right? If I divide by a larger amount, or sorry, I didn't have n increase here, right? What is n doing? N was decreasing, sorry. So if n goes down, what's happening to this fraction? It's going up. If I then divide by a larger value, my denominator, what happens to my f statistic? It's going to go, the denominator is larger, down. If the f statistic goes down, what happens to my p-value? Goes up. And then once again, I'm less likely to reject the null. Right? This was the idea. If I have smaller sample sizes, it's less accurate or less reliable. I'm going to be less likely to reject. Okay. But instead of just asking you that intuition and whether or not you're more or less likely to reject, I could ask you, if I have a smaller sample size, what happens to the p-value? Or if I have a smaller sample size, what happens to that f statistic for the joint hypothesis test? Or I could ask you about any one of these things. Okay. Any questions here before I keep? Yeah.
So you just said you can ask about anything like that. So
Mhm.
would you ask me like if sample decreases, what would the bond fraction do? Would you like ask that?
No, I was just referencing, right? What happens to the test statistic? What happens to the p-value? And am I more or less likely?
Okay.
Now, in order to determine if the f statistic increases or decreases, I need to be able to basically just think about how fractions work, right? But yeah, I would ask you about these things here, right? Not like what specifically happens to this, what specific, yeah. Okay. Any other questions on this before we keep moving?
Not related to the problem set, but the last question is literally exactly this.
Mm-hmm.
Do you just want us to answer it like in a comment, like, or do you want us running any code to prove it?
No, so in that problem set, like if you go back to like the first one, some of the questions you don't have to do in Stata, you're just answering a question, just like you would answer a question. So I'll actually get the solutions posted, that third problem set, once that due date passes. So likely Monday morning. So you'll kind of have that to kind of go back through as an additional study material. Now I'd focus more on those midterm practice questions. But some of the questions in the problem sets that aren't related to coding, like you said, literally was this question. I try to go through things in class that I ask you, right? And I could also always change these. So we work through one directional change, but I could ask you what happens if the sample size increases, and there everything would just be exactly the opposite. Okay. So anytime you're working through these practice problems, I tell all my students this, even in my introductory econ, if I give you the word increases, think through how you would solve that question for a decrease, right? Because if I give you a practice problem where I say increase, I might ask you not the exact same question. It's still the same concept if I ask you what happens if instead that increases or the opposite, whichever one I first said, I'm not forgetting. Okay? Yeah.
You know, quiz 3 has the answer for you.
So I'll post that so you can now see the answers, right? I think I had it set so it was hidden until that due date passed. I should, if it's not released, I'll double check after class to make sure you guys can see those. I usually have to change things on the back end so you can't see them until after the due date passes, and it might just have not, for whatever reason, released them. Yep. Any other questions on this before we keep going? Okay. All right. So that's some of the kind of newer stuff here, and we've kind of touched on some of the old stuff along the way. And you can reproduce what we just talked about in data to your question earlier. I can actually run this for a random sample that was a sample size smaller. So what did we say should happen to our F statistic? It should go down. Our p-value should go up. Oops. Did I already run this earlier? I'm going to drop that. I'm going to run this again. Oh, so oh gosh. I have to drop all these variables that I didn't realize I created. So just for the point of reference, we'll go back to our original hypothesis test with this 10,000 sample size. Well, if the sample size, I'm not going to answer that. They don't answer me. So If we had a really high sample size, that was going to have the opposite effects. It gave us a really large F statistic and a really small p-value, right? If instead I took a random sample of size 100, I then run that exact same regression and do the joint hypothesis test. What should happen to my F statistic? It's now not like 600, it's only 4. And what happened to my p-value? It's now higher. So we're less likely to reject. In fact, here, if I gave you this output, at what levels can you reject this joint significance test? So if the p-value is 0.015, I can reject at the 90 and 95%, because that's going to be less than my alphas of 0.1 and 0.05. I can't quite reject at 99 because my alpha there would be 0.01. It's not less than, it'd be greater than that. Okay. Any questions there? Okay. So kind of keep coming down here. We kind of talked through some of this already. So here's where we'll kind of revisit some old concepts as well. So let's say I try to run this regression. And I talked earlier about there's these 3 categories in powerlifting. You can't use any assistive equipment. You can use some. You can use like this crazy like suit they wear that makes you like Superman, right? So here's our kind of 3 different categories. If I include all of them, what issue would I have? We called it perfect collinearity, right? I have to be in one of these groups. So if I know that it's not in the raw category and not in this RAPS category, automatically I know this variable has to be a 1, right? So anytime I have something where it's a direct or a perfect function of these other variables, I'm going to have multicollinearity. What will Stata do? It's going to drop 1. Now, when Stata does this, it's going to choose one of them. I think it defaults. No, it doesn't always default. It's just going to choose 1. All right. So I was going to say, I think it defaults to the lowest, but that's not always the case. I think here, if we use like the encode command, there's some default setting. But because we've created these, we don't know which ones it's going to leave out. Right. So if I run this regression, and I just did it for the smaller sample size, just so some things might not be statistically significant. So if I'm looking here, first of all, it omitted one of those categories, right? And we'll talk about why this is a problem in a second. So first of all, which of these variables could I say have a statistically significant effect at the, let's say, 90% level? Well, what am I looking for? The coefficients that have p-values that are less than, at the 90% level, less than an alpha of 0.1. So I could say that that multiply category, male, and body weight were all statistically significant. They had an effect that was non-zero. I can't say that actually age and this category of no assistive equipment actually have any predictive power at all. I can't reject the null of 0.
You go back for thoughts.
Up here?
Yeah, so if you were to run that, I would run that, we would get the best, right?
Yeah, because every time I run these uniform distributions, it's a different random sample. So if you're trying to work alongside me with the code, focus more on the results I'm showing you because that's the results we have. Now, they should be pretty accurate, right? But they'll be a little bit off because it's a different random sample.
Close enough, we just projected that.
So it might be a little bit different than what I'm
That's what I'm saying, but Leo and I is just by chance, we got the same numbers.
So what you probably have, it should set the seed at a certain value for most, I'm guessing, unless you've changed it. But because I'm using my Stata, I've used it for things other than this class. I set the seed at some point when I was generating a random sample for something other than for class. And so it's keeping that random. You don't have to know any of this, right? But it's kind of pulling from, and that's a way that you can always generate like new random samples is by changing that set seed. If you use the same set seed, this uniform distribution would always give me kind of the same, which is why you probably saw the same results. Right? So I'm guessing you didn't run that set seed command. I ran it for a different regression. So Stata is kind of going to a different number to generate these random numbers than yours is. Okay. Is that? Yep. So here we've got not a problem, but if I wanted to know the difference between the predicted weight of that multiply or that raw category, what would I do here? Well, those coefficients on those two variables are always relative to the group that was left out. So if I want to know the difference between those two categories that were included, what would I need to do? Well, if they're dummy variables, really what they're telling me is that's the change in the predicted Y value for being in that category. So if I want to know the difference between those two categories, all I would do is take the difference between their coefficients. Okay, so that looks like it's roughly what? 110, or no, since this is negative, it would be what? 150, right? 132 minus negative 23 would be about 150, 155, right? Now, what's another way I could do this? Once again, problem set asks a similar question. Let's say I want to know, I just want a single coefficient that tells me the difference between that raw and that multiply category. There's two regressions I could run to get that. So if I want one coefficient that tells me the difference between these two categories, what do I need to make my base group? Or what group do I need to leave out? One of those two groups. Right? Now, if I leave off this raw variable, right, I include wraps and multiply, hopefully the coefficient I then see on multiply, now it's going to be relative to the group I left out or relative to that raw category. If I run this regression and I choose which variable I'm leaving out, so let's say here, I run this same regression, but instead I choose, I don't rely on stata to identify this perfect multicollinearity. I leave out that raw category. Now the coefficient on multiply tells me the predicted increase in weight lifted relative to that group I left out. If what I'm telling you is true, now that it's relative to that old group, sure enough, I get about 155. Right? I was eyeballing the values there, so I was a little bit off, but right, it should be the exact same difference. Okay. Now, if I was asked you a more conceptual question, which groups, if you have some knowledge about the variables, does it most often make sense to leave out? So I think in the problem set, if I've got income categories, I want my coefficients likely to always be compared to whatever the lowest income category is or the highest, right? So in this case, if I had some working knowledge of powerlifting, I would think about, well, if I can't use any assistive equipment, that's likely the category I want to leave out. That way my coefficients of some assistive equipment will now kind of be like increasing in the amount that I can use. Right? Now, once again, we might not have the knowledge to know that, but something like income or education levels, we would often want to leave out the highest or lowest value. Okay. Any questions on that idea before we keep moving? Okay. Oh, what do I have here? Okay, this is a good point. So let's say I run these exact same regressions, but one of them I use the small sample size. If I instead use the entire 10,000 sample size, what's going to be true? Right? So if we go here to our formula sheet, we'll kind of have to remember this little caret. So usually I use a subscript to be a little bit more, kind of make it a little bit easier, right, when we're talking through this. But that little caret above our R squared told that we were looking at the adjusted R squared. So if this is my formula for the adjusted R squared, so I could think about maybe adjusted, maybe I'll change that formula sheet to have that just to make it a little bit easier, right? So we had that was equal to 1 minus, and this is where I likely wouldn't ask you this question, but just more conceptually, if R squared is the proportion of variation we can explain, 1 minus what would give me the proportion I can explain? 1 minus the proportion that I can't explain. Right? The proportion I can explain is 1 minus the proportion I can't explain. Those have to add up to 1. We then said the adjusted R squared kind of scales up or down that proportion we can't explain based off of the sample size and the number of variables we used. So once again, we can go through this thought experiment. If the proportion of variation that I can explain doesn't change, right? Or the proportion I can't explain doesn't change. If I instead look at a higher sample size, which is what we'll do in the code here in a second, This is where it's not obvious because something's changing in the numerator and denominator. This is how I would think about a question like that. Put some hypothetical values to it. Start out with a really low sample size. So think about here, we had, I think, 4 variables. So let's think, so K was 4. So the number of variables, or I don't know, it might have been a little bit higher, but we'll just hypothetically think about this. If I had a sample size of 6, right, what would this scaling factor be equal to? 5/1, right? If instead I had a sample size of 100, what would this be? 99 over what? 95. So as I increase n, what is happening to this scaling factor? It's going to be going from 5 to about 1, it's going down. If I subtract a smaller value, what's happening to my adjusted R squared? So if I subtract a smaller value, the number is going to be, this is basic math, guys. If I take 6 and I subtract 1, if instead, sorry, 2, if I then instead take 6 and subtract 1, what happens? It gets bigger, right? I mean, that's all we're doing here, right? So if I subtract a smaller value, I know my adjusted R squared is going up, right? Or once again, if I have higher sample sizes, it's more likely I'm getting an accurate, I'm actually accurately capturing the proportion of variation I can explain. My adjusted R squared, as I increase my sample size, this is getting closer and closer to 1. If this was 1, what would my adjusted R squared be equal to? Just R squared. So as I increase n, not only is my adjusted R squared going up, but my adjusted R squared is getting closer and closer to the actual R squared, or the difference is going down. In fact, what will always be true? My adjusted R squared will always be less than my R squared. Okay. So we can prove this to ourselves with the data, but another thing that I could ask you is instead, if I keep the sample size the same, but I try to predict y, and this is where I have to give you another simplifying assumption. Let's say I add in more variables, and for whatever reason, the proportion of variation that I can't explain stays about the same, right? So if I increase k, right, and maybe this is across 2 different data sets of the same sample size. So I include more variables to predict my y variable. Once again, I just go through the thought experiment. If k, and this one's easier, if k goes up, I'm subtracting a larger value. What's going to happen to this? If I subtract a larger value, it goes down. So what happens to my scaling factor? Denominator is smaller, it goes up. If I subtract a larger value, what's happening to my adjusted R squared? If I subtract a larger value, it's going down, right? Because basically the adjusted R squared penalizes me for just throwing variables into my regression, right? So as I just include more variables into my regression, my R squared, my adjusted R squared penalizes me for that. Okay? So I could give you either a change in K or a change in N, and you should be able to say what happens to the adjusted R squared, which if you know what happens to the adjusted R squared, what's going to happen to the gap between the R squared and the adjusted R squared? Well, if the adjusted R squared is lower, that difference will get larger, right? Or kind of I'm getting a larger adjustment, right, than I was before, okay, with either changing my sample size or the number of variables K I included on the right-hand side, okay? So we can prove this ourselves, at least in terms of the sample size, right? Because we had this smaller sample size, right? If I instead increase n, we said that our adjusted R squared should be getting closer to R squared or should be going up. So if I run this for the small sample size, notice I've got a difference in my adjusted R squared and R squared of what? About 0.02, okay? Excuse me. If I instead run this not for that smaller sample, but all 10,000 observations, Well, notice this is where my R squared can change, which is why I had to give you that simplifying assumption. But if I was to run this for the larger sample size, notice what's happening to the difference between my R squared and adjusted R squared. It's now not 0.02, it's what? 0.0002, right? My adjusted R squared is increasing quite a bit, or that gap between the R squared and adjusted R squared, as I increase my sample size, is going to get smaller and smaller. Okay? So you should know how to be able to think about these equations, and you'll have these formulas on the exam, and how changes in either the sample size or the number of variables included is going to change that adjusted R squared.
And if you were to increase your variables, increase the variables?
Yeah, so as we add in more variables, what do we say is going to happen? Yeah, it's down, right? So my adjusted R squares that add in more variables go down. Yep. Or that gap is going to get larger.
Couldn't you decrease?
No. So if my adjusted R squared is lower, the difference between my R squared and adjusted R squared must be getting larger. Okay. Yep. Okay. Any questions about that before we keep moving? Okay. I don't know if I have something in the do file here, but I know something that would be important to look at. So I think here I just gave you another example of thinking about an omitted variable bias. So it might be good to go back and kind of think about what happens if I left out that variable of age. We've already done an omitted variable one. Here I want to think about, and let me see if I've got something in the data set where this makes sense. Okay, I do have one. So let's say instead, so once again, I wouldn't expect you to necessarily know this. Oops. So let's, instead of trying to predict total weight lifted, so let's say here I'm trying to predict whether or not the individual was male, okay? All right. So I've got these four different kind of X variables. I'm trying to predict whether or not the person was male, okay? I'm also going to include over here the total amount of weight they lifted, okay? So I run this regression, all right? I kind of have all these. Now, this is where if I have a dummy variable as my Y variable, how do I interpret all of these coefficients? So let's think about maybe that total weight lifted that was in kilograms. How do I always interpret a coefficient? It's a 1 unit change in that X variable. So if the person lifts 1 additional kilogram, the predicted value of Y changes by that coefficient. But if Y is a 1-0 variable, the change in Y would be here an increase in the probability that they are the one category or that they are male. So for every additional kilogram lifted, the probability that the individual is male goes up by 0.002 or 0.2%. What did I forget to add in there? It's a multiple linear regression. I then have to hold everything else constant. Okay. Now, we talked about an issue that can exist. So in powerlifting, so I've got, let's do, the thing that all the bros care about, which is your bench, all right? So let's say I also include not the total amount of weight they lifted, which was across 3 different lifts, but I included one of those lifts specifically, which was the bench press. Well, inherently, if I bench press more, the sum of the 3 lifts has to go up. They are directly related. Now, the total amount lifted, I still could see different bench values. So they're not perfectly collinear, they're imperfectly collinear. Okay? So if I have imperfect multicollinearity, we said in general, and this is probably something you just need to memorize. Okay. If we have imperfect multicollinearity, if I run this regression, the standard errors on one of those variables that are imperfectly multicollinear should go. Let's think about it. Maybe a good way to memorize this. If I'm running a regression and there's an issue, it's likely going to make me less likely to reject something. So if I have this issue of imperfect multicollinearity, one of the standard errors, well, if I'm less likely to reject, the standard error must be going up, driving down my test statistic, increasing my p-value, making it less likely I can reject. So I know if I have imperfect multicollinearity, which of these two variables could have an issue with the standard errors, the ones that are imperfectly multicollinear. All the other variables shouldn't matter. Right? They might change a little bit, but we don't know if they're going to go up or down, right? So if I run this regression where I instead include this variable where I now have some imperfect multicollinearity. So if we look at some of these other coefficients, still about -0.2, still about -0.05. They do change a little bit, but in terms of the statistical significance, they're pretty much the same, right? -6 is my test statistic, -26 instead of -24. But notice when I look at those two variables that are imperfectly multicollinear, right? Compared to, or where did I have this? So this is body weight. So this is before I included that bench variable. So it's not quite statistically significant. It has a p-value of 0.63. Notice here, when I include both of those variables that are imperfectly multicollinear, so here's where it not always increases my standard errors. It doesn't necessarily increase them, but what it will do is it will incorrectly estimate what that standard error is. We didn't go into why I would increase or decrease it. All you need to know is that it impacts one of those variable standard errors by a lot, right? So in fact, when I only included body or total weight lifted, I had this p-value of 0. Now that total weight lifted, it's still 0, but notice what happened to the test statistic. It went from 80 to about 18. So even though it looks like the statistical significance didn't change, it went down by quite a bit, right? At our conventional levels, it didn't change, but going from a test statistic of 80 to 17, it's a pretty dramatic drop off. What caused that is our standard errors, instead of being 0.00002, are now 0.00006. So it increased them by 3 times, right? They're small values, so it doesn't look like much, but they're now 3 times as large. So if instead I had a standard error before, it was like 0.5, that would be like giving me a new standard error of 1.5. So when I run this regression with imperfect multicollinearity, one of these estimates is going to be wildly off. Now here, why might I didn't change my rejection decision? Because what also is going to impact my standard errors? My sample size, right? So if I go to this regression, if I just go back to thinking about, here we are, my standard error equation, it's always n minus 2. So if n is really large, my denominator is really large here, what's going to happen to my standard error? It's going to be really small, right? So regardless of the fact that my standard errors went up because of this imperfect multicollinearity, my standard errors are still going to be pretty small, right? Because I have such a high sample size. So maybe a better kind of thought experiment here was, let's say I do this exact same thing. But I run it for the smaller sample size. So here was my, I flip these. Yeah. Oh. So here I don't have that imperfect multicollinearity issue. Now I do. So now if I look here, when I left out that variable, I have a p-value of 0. When I included that variable that is multicollinear, what happened to my standard error? It went from 0, sorry. What happened to my p-value? It went from 0.1, or my standard error went from 0.4 to about 0.0006. Right? So it changed that standard error quite a bit. And this is where we don't know if it's going to go up or down. We just know that that standard error is going to change a lot. Now, here's where I wouldn't ask you a question like this because it's not fair, right? But by including this additional variable, what did I also do? If it was important, I've eliminated omitted variable bias. So not only will my standard error change, but what's also going to change? My coefficient, which is part of what goes into calculating that test statistic. So with imperfect multicollinearity, all you need to kind of expect to know is that it's going to alter the standard error of one of your estimates by a lot. And in fact, it's kind of difficult to kind of know which one. So maybe the standard error wasn't being impacted for this total weight lifted variable. It could have been that it was the bench variable that had the standard error being too high, which might have led to an incorrect p-value there. So kind of revisiting this idea of perfect and imperfect multicollinearity is something else I wanted to make sure we did today. Okay. We got 10 minutes left. Any other questions you've had over anything we talked about today? Okay. So we've got this practice exam, probably worth at the beginning of next class on Tuesday, revisiting what I shouldn't call this easier, but older material that might now seem easier, right? So here we're talking about, you know, the relationship of means to median and skewness output from stata. We're talking about simply looking at, is a sample mean different than a certain value? Now you'll notice on the practice exam, only the first 3 questions are related to anything other than linear regression, right? We were kind of building that base so that we could get to linear regression and very easily talk about these test statistics and p-values, right? And the role of sample size, et cetera. So the majority of that in-person exam is going to be all the topics related to what we talked about with linear regression, okay? So I would come to class Tuesday. I would try to at least skim through or look at this practice exam and identify things where you might have questions. Now you have the answer key, so hopefully skimming that, identifying those is a little bit quicker. Now it's obviously good. I always tell my B251 students, I give practice exams, and I thought the same way when I was a student, and it's probably because I should call them something different. It's not practice in that you should sit down, take the exam, because is that going to help you learn the material any better? No, just be like if you sat down and took the actual exam. What does the practice exam and me giving you the answers do? It allows you to come up with solutions to these problems as to why the correct answer is what it is. Now, if you want to go through and take it to give you an idea about where your understanding is, that's still helpful. But the real usefulness and the real marginal benefit from a practice exam comes from the fact that you can identify what you don't know and then try to use your notes, things we talked about in class, go back to the old videos, and provide a reason or a solution why that correct answer is what it is. Okay? So that's how I would think about these practice problems. Now, you could also go back to the old quiz questions, especially once I make sure that those solutions are out there. But I know the 1 and 2 are out there, so you can kind of go back. You can also go back to those old practice problems. We kind of do a similar thing working through those. Now, the first thing I would do is work through this set of questions on the practice exam. Those are going to be probably more likely to look like, you know, try to structure this and give you the types of questions you would see on the actual exam, right? So if I was doing it in order of like marginal effectiveness or the marginal benefit of my studying, I would go review that practice exam, review the old quizzes, review the old practice problems. Also, reviewing the old problem sets. So once again, I'll get those solutions posted after the due date passes for problem set 3. I also will kind of get that problem set 2 solution posted. There were some issues with one student, so I was holding off on that. And so those will be kind of posted. Now, obviously, I wouldn't go back. I shouldn't say wasting time, but I wouldn't go back and try to like go through the code for those problem sets. I would try to go back to some of those questions that were, to your point, I didn't really need to run any code. It was more of a conceptual question. There aren't as many of those on the problem set, which is why I kind of mentioned that last. So I would put that all the way down at the bottom, right? Yeah.
How many would you say are MCQ?
So I mentioned this on Tuesday. What's going to be true about the in-class exam? It's all short answer, all written response. What am I going to do other than that? I'm going to post a take-home multiple choice exam, which I'll open it up after the exam in class, and that'll be due at the end of the day the following Monday. So you have a few days to kind of go finish that. It will be weighted, working on finalizing the points, but it's going to be approximately 25 to 30%, right? So the bulk of the exam is going to be what you do in class. Okay? Any other questions related to the exam, kind of logistically? Like I said, Tuesday, hopefully you're coming to class. Should come to class because we're just going to be doing review and you can then ask the questions. Probably, I don't have anything. Literally Tuesday, I have nothing planned, right? I plan to be here. And as you ask me questions, if it's on old quiz, if it's on the practice exam, old practice problems, I'm going to work through those one by one, right? We're not going to look at any do files like we did today. I was just kind of using those do files. Problem set still technically can be turned in by the end of the day tomorrow, but also to kind of revisit the state of output. And really they're focusing not on the code, but the actual output, because that is what I could give you, just like here. What am I doing? I'm copying, pasting state of code, right? Or state of output, the code and the output. Okay. So any other logistical questions for me before we kind of finish up here? And if you think of any questions, once again, Tuesday will be kind of met for review. It's a good time. I kind of went through any lesson in my B251 class today where asking questions are public goods. And so what do we kind of have people do? We fall victim to the free rider problem. Everybody else hopes someone else asks the question, right? Because there's a huge cost at looking dumb in front of the class. Do not feel dumb. There's no easy. I mean, a lot of this stuff, the stuff that I said was easy, we're also really far removed from it, right? So it still might be good to go back and ask questions about some of that earlier stuff that maybe should be less difficult concepts, but we're pretty far removed from it. Right? Now, the other thing, you're going to want to definitely listen to this, okay, before you leave class today. What I've got up here on Canvas under module 7, I guess I'll move it down here to be under that midterm exam. So you can complete this before you leave class today. You can complete it basically by the end of the day today, okay? So what this has is a set of questions that if you answer all of them, I will add 3 points to your exam. So if you got a 90, you get a 93. Right? It's basically almost bumping you up a letter grade in terms of the exam, right? A minus to an A, right? So this is going to help me also if people don't want to ask questions and we fall victim to the free rider problem Tuesday. It's going to let me know what to focus a little bit more on. It also gives me some data that I might use, or maybe we'll look at. Obviously, I'm not going to include your names in the data set, but it lets me kind of see what the correlation is of certain things with exam performance and kind of maybe where some of the things that we need to spend a little more time on even after the exam are going to be. So I've got these different kind of categories, some things we talked about today, some things we didn't. So what do you find the most difficult? One being the most, and then kind of rank them accordingly, right? So in like Canvas, you can kind of move these around so that you change the ranking, one being the thing you find most difficult all the way down to the kind of very bottom, right? Now, I get that these are just, you can get the points if you just simply fill them out. This is going to be more useful to you if you actually stop and think kind of hard about this, right? Because it's going to allow me to kind of direct class a little bit more on Tuesday, even given the questions you ask. I know which ones I might focus a little bit more on and which ones I might gloss over a little bit based off people's responses, okay? I then kind of have how many class periods have you missed? Once again, this is kind of collecting some data, so maybe we can make some statements about how important class is. Now, I can look at how many in-class quizzes you've missed, but we don't do those every class. So be as honest as you possibly can. So we'll talk later on after the exam about something called measurement error. Might use this as an example, right? So because I know some people are going to probably lie to me, I might have some measurement error in this, but I'm not going to look at any one specific person. I'm going to look at the collective total of this. So don't worry about me like looking to see, oh, how many exact class. Try to be as truthful as possible. This gives us a better idea about what we can kind of do in the second half of the class, okay? And then I'm interested here. I'll talk a little bit more about this probably after the exam, but I'm taking a course actively on generative AI and how to use it in the classroom, and also just trying to learn more of the backside of AI because I've run some of our stuff and I know some of you are using it to create those do files. I know it because I've seen some things, some common errors that you're getting incorrect because you're trying to do things at a level of difficulty that are outside of what we're doing. And that's actually going to just progress in the second half, right? So I want to rely less and less on those. Also, the more you rely on them, probably the less likely you're going to retain a lot of that information and maybe your exam performance won't be as high. But they can also be a very useful tool. I'm not going to say you should never use them. In fact, I think if we learn how to use these generative AI tools, I think it actually can improve your learning and understanding in any topic, any course quite a bit, right? It's just that's not the goal of my course, right? I spent a whole semester teaching you how to effectively use AI, right? And then kind of what score do you expect on the exam? We then might kind of think about expectations versus performance and kind of think there. I'm just kind of wanting to get some more data so I can think about how to kind of cater this class in the second half a little bit more, better for you guys. Okay. So this needs to be filled out and completed by the end of the day today to get those 3 additional points added to your exam. Okay. So this is also a value of showing up to class. You now know about this, right? So have a fun, safe weekend, and I will see you guys on Tuesday. Sorry for the technical issues once again. I'll